Swayam Prabha. Digital India. Educated India.
Welcome to Organic Chemistry, Paper 3. In Unit 3, we are studying about heterocyclic compound. In Lecture 7, we will study about Indole. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayamprabha, MHRD, New Delhi. The topics that will be covered include the structural elucidation of indoles, and we will also be looking at the various synthesis of indole. We will mainly focus on Fischer indole synthesis and Madlung synthesis. Welcome to the session on indole. So let us start with indoles. Indole is a fusion of benzene and a pyrrole ring. So here is the benzene ring which is fused with the pyrrole ring. There is a 5-membered nitrogen heterocycle. So these two are fused together, and this fusion is called the indole ring. And indole is actually the main photoconstituent across various plant species. So that's the reason we will also look at how the indole name was given. We will look at, and some of the amino acids like tryptophan. If you look at the indole moiety, it is widely present in various biomolecules. Say for example, tryptophan, which is an amino acid, has the indole moiety. So here is the indole moiety that is present in the tryptophan. Serotonin and melatonin, which are animal hormones, they also have the indole moiety. So here we see that indole moiety. Vinblastine, vincristin and vinorelbine, these are all the various alkaloids that also have the indole moiety. So indole is widely present in various biomolecules. Similarly, indole is also an important moiety present in various drugs. Sumatriptan is one drug which has the indole moiety as shown here. So this drug is used for the treatment of migraine, and ondansetron is another drug which has this indole moiety here. This is a substituted indole moiety, and this is used for the suppression of nausea and vomiting caused by cancer chemotherapy and radiotherapy. Lysergic acid and its derivative also has this indole moiety. So these are some of the examples of the drugs where indole moiety is present, and ellipticin, yohimbine, indomethacin are some other drugs where indole moiety is present as a crucial unit. So here we see this indole moiety. This is a substituted indole moiety, and yohimbine has indole moiety at one of the terminal site. So as I mentioned earlier that the name of indole has something unique to our country. So basically the dye, indigo dye, which is a blue dye, was first used in India, and the structure of this indigo dye was deduced to have some of the indole structures. So from indigo, isotin was formed, and isotin was converted to oxindole, and Adolf von Baer converted oxindole to indole, and that is how he gave the name Ind. That Ind came from India, so the indole compound's name was given. So the molecular formula of indole is C8H7 and N. This indigo on oxidation gave the isotin, so that is how they found out the structure of indole, and isotin on reduction gave hydroxyindole. The structure of the things are given here. So basically, use of nitric acid for the oxidation of indigo led to the formation of isotin unit, and this isotin was then reduced to give dioxindole, and this was further converted to oxindole, and from oxindole indole was finally prepared. So Adolf von Baer worked on this, and he finally deduced the structure of indole. So that's the reason he gave the country name India to this compound as indole. So let us look at the structural elucidation of indole. This indole does not undergo addition reaction. So when halogens or HX was treated with indole, it did not undergo addition reaction. So this is point number 1. And this also does not decolorize alkaline KMnO4 or bromine water. And this compound was a very stable compound. It has a melting point of around 52 to 54 degrees centigrade, and this undergoes electrophilic substitution, which shows the presence of aromatic ring. So we are actually listing what are all the various reactions that are given by indole, and based on this we are going to identify what is the structure of indole. And oxidation generally gives 2-formyl amidobenzaldehyde. So that means indole, we really don't know the structure of indole. This on oxidation using alkaline KMnO4 actually gives the compound which is having the structure as shown here. This is 2-formyl amidobenzaldehyde. So there is a formyl group, that means that there is an aldehyde group that is present, which is ortho to a, if there is one hydrogen additionally, so this is nothing but the amino unit. So one of the hydrogen is replaced by an aldehydic unit. So this is what is called the amido derivative. So the amido derivative, and if this amido derivative is not present, this is basically the benzaldehyde derivative. So in the ortho position, this formyl amido derivative is present. So that's the reason we give this compound 2-formyl amidobenzaldehyde derivative. So the formyl name is given for this particular aldehydic group. From this, what we can deduce is there should be 2 rings, or maybe there are more rings. But when we look at the molecular formula earlier, we only have C8 carbon. So that means we cannot have more than 2 rings. So one ring most probably may be having a benzene type unit, because this compound undergoes electrophilic substitution. So that means there is one aromatic ring that is present in the compound, and this oxidation shows these are actually having 2 ortho substituents are actually present. So that means the fused ring has a structure where the 2 groups are attached to the adjacent carbon atoms. And when we completely reduce indole, what we end up is a octahydro derivative. So when do we get the octahydro derivative? There should be 4 double bonds. So this also gives another indication that this compound is a bicyclic compound, and there are 4 double bonds present. So from that we can, and of course another important information what we have is from the anthranilate. That means this is a alpha amino, there is a amino group in the ortho carbon atom. So ortho amino benzoic acid is nothing but antranilic acid. So from the biosynthesis of antranilate, that means the carboxylate anion is a starting material, that is the antranilate is the starting material for synthesizing indole. That tells that there is a carboxylic acid unit which is ortho to a amino group. So this is one information we are having additionally. So that means there is a benzene ring, and the benzene ring is actually disubstituted, and one amino group, and another one is a carbon atom. So based on that reactivity and whatever we have seen earlier, we have multiple structures. That means starting from A to G, we have various structures that are possible for indole. So what are all the information we already have? Indole on alkaline KMnO4 oxidation leads to a compound that is having a aldehydic unit, and formyl amido group is also present. So these are all the 2 things we already know. So that means all these compounds, if you look at, they all can undergo this particular oxidation to give this kind of compounds. And of course we have additionally a compound with 4 double bonds and 2 rings, that is another thing. So if there are 2 rings are there, or whether it is only 1 ring is there, is very difficult to find out. So that is the reason we can also consider the presence of a linear alkyne type unit. The structure C will not give the formamido derivative, and it also gives the decahydro derivative on hydrogenation. the final indole is actually formed from the anthranilate. So the biosynthesis starts from this one. That means it should actually have a aromatic ring. So if you look at all these structures, the structure E, structure F, these and the structure G, all these three cannot be the structure of indole because we do not have an aromatic system. That means the substitution reaction which are shown by indole cannot be explained by these structures. So we can completely rule out these kind of structures for the indole moiety. Another thing is we have structure A and structure D. If you look at the structure A and structure D, we have still 4 double bonds are present here, and there is in one of the ring nitrogen atom is present. But what we have studied so far is nitrogen ring, where nitrogen is present in the heterocyclic ring, that compounds also undergo electrophilic substitution. So that means there is a possibility that this compound can be having structure D also. But if we look at the oxidation product, this compound cannot give the required or the formed oxidized product. So that means the nitrogen is not present in the 6-membered ring, so it should be present only in the 5-membered ring. So in other words, we cannot have the structure D for indole. So this is also ruled out. And when we come to the open chain structure, this is a probable structure that can actually give the required oxidized product as shown here. But this compound cannot be formed from the anthranilate starting material. So we can completely rule out this C is not the structure for indole. And then we are left out with the structure A and B only. So in the B, the nitrogen is actually in the 2 position. So if it is in the 2 position, then we cannot explain the oxidation product formation. So in other words, the structure B is also ruled out. So when we rule out all these structures, the most probable structure for indole is given as the structure 1. So here we can explain all the observed reactions. Say for example, this on oxidation can lead to an aldehyde group forming here and another aldehyde group forming here. So that means the oxidation products can be explained by this structure, and this structure has 1, 2, 3 and 4 double bonds are there. So in other words, we can explain the octahydro derivative as the final hydrogenation product that can be explained. And also we can also explain this anthranilate to this structure, because here both the atoms are connected in the ortho position. So the structure of indole can be confirmed to be given as in the structure A. And how do we confirm that? We can actually carry out the synthesis of indole to confirm what is the proposed structure, or the structural elucidation can be confirmed by the synthesis of indole. So here are lots of methods by which indole can be prepared, and we will be mainly focusing on only 2 reactions, that is the Fischer indole method and the Madlung method. So other methods are actually given here. We have actually given 2 rings because indole has 2 rings. So the heterocyclic 5-membered ring is given the number 1, and the other 6-membered benzene ring is given number 2. So we have various bonds. So if we look at the retrosynthetic scheme or a probable way of forming this bicyclic compound, we have various permutation combinations possible. That means in one combination, say for example 1A and B. So in the structure 1, A and B are the forms which are actually formed with one particular unit which is coming from the outside. So that means this is one way of forming this compound, and another one when we say 1AC, so that means the bond A and the bond C is actually formed, and the other unit comes from this kind of starting materials. So this is another way, and we can also form the benzene ring from other reactions. So the 6-membered ring also can be formed from various other reactions. And mainly we will now focus only on the Fischer indole synthesis, where this particular bond is the one that is in ring structure 1. The C bond is the one which is formed, a single bond formation we will study, And we also will study about the 1b bond formation. That means this double bond formation. Here we are going to connect these two bonds. So that is using the Madlung method. So we are going to look at mainly these two reactions. So let us look at what is Fischer-Indole synthesis. So according to this method, by using Lewis acids or acid catalyzed reaction, especially the rearrangement reaction of aryl hydrazone leads to the formation of indoles. So here there is a loss of ammonia happens. So we have two nitrogen atoms. If you look at the aryl hydrazone, we have two nitrogen atoms, and out of two nitrogen atoms, one nitrogen is lost as an ammonia molecule, and we end up with the final indole product. And here whenever we have a electron releasing groups, that means anything which is giving electron towards this ring actually facilitates or increase the reaction rate. So any electron donating group that is present in this particular ring increases the rate of the reaction, and when an electron withdrawing group is meta to the nitrogen, say for example this is the starting that aryl hydrazone, when we say it is meta, then we actually go from this side. Let us say this is 1 and this is 2. If the second carbon some substituent is present, this is what is called the meta position, and when there is any electron withdrawing group that is present in this particular 2 position here with respect to this hydrazone's nitrogen, then that is basically this is the aniline starting material. So in that particular hydrazine is the starting material. So in this particular case we have two types of cyclization possible. Let us put this number like 1, 2, 3, 4, 5 and 6. If we put a number like 1 to 6 like this, then in that case we can actually have the cyclization happening at this carbon, or the cyclization can happen at this carbon. So these are all the two places at which the cyclization can actually lead. So when that happens, we are going to have different type of substituents, like it is mentioned here 4 and 6 substituted indoles are possible. So that means when the cyclization occurs, we may end up in one reaction because the meta position is going to be the product. So with respect to this one, the meta position is here if the cyclization occurs here, and the same compound, the same meta oriented product will be here, and the cyclization can also happen from this side also. So there are two ways by which the cyclization can actually happen, and depending on that where the cyclization took place, we have 4 and 6 substituted indoles are possible. So let us look at the mechanism for this particular formation. So this is our starting hydrazone, aryl hydrazone is given here. So how an aryl hydrazone is formed, as you already know, there is a carbonyl compound, carbonyl oxygen is there. Here we have the phenyl hydrazine, two hydrogen atoms are attached to this, nitrogen is present. So normal hydrazine is NH2, and in this hydrazine, one of the hydrogen is replaced by a phenyl group. So that is why we get the phenyl hydrazine, and when the phenyl hydrazine reacts with the carbonyl compound, especially in this particular case we are this is a methyl group. So we have a acetophenone is our starting material. So we end up with this particular phenyl hydrazone that is formed. So this is our starting material, and in the presence of zinc chloride at 170 degrees centigrade, what happens is there is a proton transfer actually takes place. Proton transfer is the first reaction. So the hydrogen from this methyl group, one of the hydrogen from this methyl group shifts from here to this particular nitrogen. So that is where we get a double bond here. So that means there are two hydrogens are there, and this nitrogen gains one hydrogen atom. So the proton transfer is the initial step, and once the proton transfer happens, there is another addition, because this is a Lewis acid catalyzed addition. So there is a H plus ion addition that happens to this NH carbon. So this NH carbon again takes one more proton, So when that happens, we end up with the NH2 plus ion here. So the shift of bond takes place as shown here. This is a 3 plus 3 3 sigmatropic shift, and this leads to this particular intermediate. This intermediate is actually non-aromatic intermediate. So this is an aromatic compound. The aromatic compound is converted to a non-aromatic compound. So this is quite unstable. So to stabilize that, what happens is one of the hydrogen is lost as a proton. So in this step a proton is added, and in this step the proton is removed. So that leads to the formation of the amino unit. NH2 group is formed, and this nitrogen is actually having a lone pair of electron. So this attacks this carbon because this NH2 group is now having a positive charge. Nitrogen, as you know, is more electronegative than carbon, so it cannot have the positive charge for longer. So this pulls the bonded electron towards itself. So that is how this bonded electron is pulled towards this nitrogen atom, and that makes this carbon positive. We end up with a carbocation here. Since there is a carbocation here, the nitrogen's lone pair of electron is actually going and attaching itself to this particular electron deficient carbon atom. So we end up with the cyclized product. So the cyclization takes place at this particular step, and as we have seen earlier also, one of the crucial step is the formation of aromatized product is the driving force for the final product formation in most of the heterocyclic synthesis. So similar to that, here the hydrogen is lost as a proton. So these bonded electrons are now shifted between this carbon and this adjacent carbon, and now NH3, because this hydrogen actually whatever is lost from here comes and attaches itself with this NH2 plus, and that leads to ammonia molecule that is being lost. So final step is the loss of ammonia molecule, and this leads to the final cyclized product, that is the indole is formed like this. So this is the overall mechanism for this reaction, and in this reaction we are having a loss of ammonia. So this indole, as we mentioned earlier also, there is a regioselectivity that is possible in this reaction. Here we are going to look at the regioselectivity with respect to the carbonyl compound. So we are going to use a carbonyl compound. We have two groups that are present. One is a methyl substituent, another is a ethyl substituent. So we have two different substituents that are present in the carbonyl compound, and based on these two groups we are actually going to get regioselective product formation, and we are going to look at how the regioselectivity is being governed, what are the factors that affect these kind of products. So here, as we know, the first step is the formation of the phenyl hydrazone, and once the phenyl hydrazone is formed, we know the next step is the alkene, that is the olefin formation. So through the proton transfer we end up with this particular intermediate, and this intermediate can now undergo cyclization to give product A. So here this is actually the 1, 2, 3. So 2,3 dimethyl substituted product is formed, that is indole is formed. And the other case is there is a methylene carbon is actually losing or giving that hydrogen. That means we have methyl group that can actually give the hydrogen atom, or shift of hydrogen takes place from that group. So this path is methyl group gives that hydrogen to the nitrogen, and in the top we had given it is the ethyl group. So ethyl group means it is basically CH2 and CH3. So from this CH2 group one hydrogen is given to this nitrogen. So we have the double bond as shown here. So when the methyl group hydrogen is shifted, we have the double bond, external double bond is formed here, and that leads to the product B. Here we have the 1, 2. The 2 substitution is basically ethyl group. So instead of 2,3 dimethyl indole, we are getting a ethyl indole, 2 ethyl indole. So these are all the different ways, and here which tautomer will be formed, because we have two isomers that are possible in this reaction as an intermediate, and this tautomer formation is actually dependent on whether the hydrogen from the methyl group is lost or the hydrogen from the ethyl group is lost, depends on the reaction conditions. So, if you are using acetic acid for this particular reaction, then the product A is formed in 100%, and when we use methane sulfonic acid and phosphorus, otherwise P2O5, that is dimer of P2O5, phosphorus pentoxide, if you are using, that gives B as the major product, that is 78% of B is formed. And when we use simply PPA, that is polyphosphoric acid is used, we get 1:1 ratio, that means A and B are formed in 50-50 ratio. So, depending on the reaction condition, we can get different types of products. So, this is how the regioselectivity is controlled in these kind of reactions. So, the next one is the Madlung synthesis. So, in this particular process, indoles are actually prepared from N-acyl orthotoluidine. So, that means these are nothing but ortho substituted aniline. So, we have a ortho substitution, and if the acyl unit is not present on this nitrogen, this is nothing but the aniline, simple aniline. So, in aniline we have a ortho substituent, and the amine is also acylated. So, that is the reason the starting material is N-acyl orthotoluidines or ortho substituted anilides. When these are heated with the sodamide, 2 equivalent of sodamide is used in this reaction at 250 degrees centigrade, that leads to the cyclized product, that is indole is formed. Why we have to use a strong base, that means sodamide is being used in this reaction? The reason is like this particular hydrogen atom on this methyl group is very weak acid. So, to abstract this proton, we need a very strong base. So, that is the reason we have to use sodamide as the base in this particular case. Its pKa is around 38, and this reaction actually involves 2 equivalent of a base and a very high temperature. So, we call this as a very drastic conditions, but even then this gives a reasonable yield for this unsubstituted and alkyl or aryl substituted ring systems. So, this is one of the advantage of using this particular harsh condition, and here if the substituent is either alkyl or aryl, they are formed very nicely, around 60 to 80% of the yield of this final substituted indoles are formed. So, this reaction is preferred reaction for the formation of alkyl and aryl substituted ring systems. Let us look at the mechanism for this particular reaction. So, as we have mentioned, there are 2 equivalents of the base that is used in this particular reaction. So, why do we need 2 equivalent of the base? So, the presence of this primary anilide group. So, this is what is the crucial one. This actually takes up 1 equivalent of the base. So, the initial step is not the abstraction of this particular methyl hydrogen, but the abstraction of the amido nitrogen is the first step. So, that is the reason we completely use 2 equivalent. The first equivalent is used to abstract the amido hydrogen, and once this is abstracted, then the second equivalent of the base is actually used to abstract the methyl hydrogen, and this leads to actually our actual reaction. So, an anion is actually formed, and this anion can now attack the electrophilic carbon, and this oxygen being electronegative pulls the electron towards itself. So, we end up with this cyclized product. So, if you look at the number of steps, the first step is the base abstraction of the amido hydrogen. The second one is the benzoylic hydrogen is abstracted by the base. Then the benzoylic anion attacks the electrophilic amido carbonyl, leading to the cyclization. So, this is the crucial step in this particular process. And then what happens is, the next step is the protonation of the amido nitrogen. So, that means the negative charge on nitrogen is now neutralized by the proton. So, we end up with the NH unit as a neutral one. and the oxygen is having a negative charge. So, this is also neutralized by the abstraction of the hydrogen atom. So, this oxide is now converted to the hydroxyl ion, and this hydroxyl is then converted to the hydronium ion by another proton abstraction. So, these two leads to the formation of H2O plus, and this H2O plus is a very good leaving group, and the loss of hydrogen from the adjacent carbon leads to concomitant removal of the water molecule that gives the aromatized product. So, the double bond is actually formed in the final indole. So, this is how the overall reaction for the Madlung synthesis proceeds. So, there are also some variations with respect to Madlung synthesis because the temperature what we have seen was around 270 degree 250 degree centigrade with the 2 equivalent of a strong base like sodamide is being used in this reaction. So, this is a very drastic condition. So, people had modified this by some other introduction of some additional groups. Say for example, introduction of a electron withdrawing group in this benzylic carbon actually increases the acidity of this particular proton. So, once the acidity of the proton is increased, we can actually use a weaker or a milder base. Of course, tertiary butoxide itself is a very strong base, but compared to sodamide, sodium tertiary butoxide is not a very strong base. So, in this particular case, we can actually use a much less strong base compared to sodamide, and also the temperature of this reaction can be carried out at a lower temperature. So, that is the reason introduction of electron withdrawing groups on this methylene this benzylic carbon increases the reactivity of the substrate. So, here the triphenyl phosphonium substituent converts the reaction to an intramolecular Wittig type reaction, and it yields a 2 substituted indole like the previous case. Let us recap in this summary what we have studied so far. We have studied about the structural elucidation of indole. So, how the bicyclic structure of indole can be deduced, we have seen. Based on various reactions of indole, we identified what is the probable structure of indole, and then we have confirmed the structure of indole using synthesis. We have studied about Fischer indole synthesis and Madlung synthesis. What are their applications we have seen, and what are the different substituted products that can be formed from these two reactions, that also we have seen. With that, we conclude this session on indole. Thank you.